Okay. So again, someone taking up from our last class, our last review of concepts, what is this right here? I'll give you a hint. It allows a lot of networking functionality and encryption functionality to be possible, right?
It's XOR.
XOR is correct. Thank you. Excellent. The multiplexer allows us to do what with inputs?
Select inputs.
Select or switch between inputs. Excellent. Thank you. So I sub 0 is our first input, and I sub 1. We can, with a single bit, decide whether we're accepting this or accepting that. Another innovation, huge. Okay. The D-Mux allows us to switch between multiple outputs. So it is analogous or similar in nature, but it's not like we can trace back to see what the input was. It's not the absolute reverse of a mux. Its function is similar. Okay. Remember that you can create XOR logic gates in a variety of ways, and there are occasions where using fewer components is desirable and using more components is desirable, depending on the context, right? Has everyone had a chance to see what's going on with the links? Don't answer that question. We have explained that the XOR allows us to identify cases where what happens with the inputs. There is a certain case with the inputs, and the XOR returns a true or 1 or on. It lights a bulb. It turns on an indicator. It says, yes, this is happening. What are we talking about with regard to the inputs?
When the inputs are different.
Correct. When the inputs are different. Who is it that's on fire this morning?
Michaela.
Michaela. Well, whatever coffee you've had this morning, I'd like a cup of it. You're really on point. Outstanding. Thank you, Michaela. Yes, when there's any difference in the inputs, this lights up. XOR rather, is the reverse of that. Someone else, please. This lights up when what other condition is correct or true? There's a truth table right on the screen. Come on.
When both are true.
When all of the inputs are what? When both are true, but there's that is correct.
When both of the same, I mean both are false or both are true.
Yeah, when all the inputs are the same, it lights up. So XNOR lights up when all the inputs are the same, whether false or true. XOR lights up when any of the inputs are different. And those are fundamentally profound in terms of the effect that it renders for components. This is a symbol that I want you to become intimately familiar with. We have the dot, which represents what basic logic gate? The simple dot. And is correct. The plus sign represents OR, and this represents XOR, right? So if you see this symbol, it means there's an XOR in the mix, right? So we have said that NANDs are used to make flash memory chips for solid state hard drives and thumb drives, right? USB thumb drives, and NORs are used to make BIOS chipsets in most modern computers, right? But you can create any of the basic logic gates using either NANDs or NORs. There are advantages to using NANDs based on this particular interest. And there are advantages using NORs for this particular interest. The BIOS chipset is a special integrated circuit that sits on the motherboard. Does everybody know what we mean by BIOS chipset? Yes, no, maybe?
Maybe.
So when you boot your system, when you power it on, it goes through a power on self test. It's called POST, power on self test. Repite usted, por favor. Everyone. Power on self test.
Power on
Self test.
what? Soft test?
Self test. POST.
Self test.
POST. Power on self test. And what's happening is that it runs checks, it runs function checks with each of the physical digital components on a computer. So it runs out to the display, it runs out to the keyboard, it runs out to the mouse, it runs out to the hard disk, it runs out to the network card, it runs out to the memory, it runs out to the CPU, it runs out to all these different components in a system board. And it basically says, is this good? Check. Is this good? Check. Is this good? No. Might not be connected, right? It enables a computer to properly initialize the startup process. Now, you can enter a setup access utility, which is called the BIOS setup. Sometimes BIOS is referred to as firmware. But here's an image of the chip. You have this little chip on the board, and there's usually a system battery. And the system battery, it looks like a little button cell. That keeps power on your computer active when it's turned off and disconnected from power, so that the system clock, this is what keeps the system clock, the date and the time, intact when your computer or laptop is powered off. This gets old, and what can happen is that when you start up your machine, you get a message from this BIOS setup screen that says, press enter to initialize your date and time. And you'll notice it goes all the way back to like the year 2000 or from 10 years ago. And it says January 1st, first month, first day, first hour, 1 a.m., January 1st. And it's like some years ago. That's your indication that the button cell is old and has died, and all you do is go to the favorite hardware store or pharmacy, and they have these because they use them for other reasons, like key fobs that you use to open your car, or hearing aids, right? Or smoke alarms in some cases. But you buy one of these button cells, you pop it in there, and then you put the data in, and it doesn't lose the date and time anymore. This chip, this BIOS chip, is in some cases sensitive to ultraviolet light. It is made from a programmable random read-only memory. ROM means read-only memory. RAM is random access memory. ROM is read-only memory. And an EEPROM is an electrically erasable, EEPROM, electrically erasable read-only memory. You can shine a black light on it and it blinks out the BIOS and all that disappears. And then you have a brick. It's called bricking your system. You've ruined your system. It won't even boot. It can't do the the power on self-test. It's dead as a hammer. Right? That's what we mean by this BIOS chip. Can everybody see this in particular?
Yes.
Yes.
So if I had a BIOS chip that did not have a window, it would not be one of these electronically erasable read-only memory BIOS chips. But here you see, and this is a telltale sign, when you see a BIOS chip with a clear window or crystal, that's on purpose. So that when you shine the black light, the ultraviolet light, for so many seconds, it melts the ones and zeros that are in that circuit, erases it. And sometimes you need to erase something like that before you flash it. When you load that chip, when you load a BIOS chip, it's called flashing the BIOS. You're loading it in through the utility access here, and you're loading new firmware on there, and it is persistent, or what we call non-volatile memory. RAM is considered, random access memory is considered volatile memory, because when you turn off the computer, what's in RAM after 60 seconds just disappears. When you turn this off, it doesn't disappear. And its main intent isn't to be read from and written to constantly. You're going to put firmware in there, and that's where the firmware is going to sit until you have to update the firmware. When you update the firmware, you are flashing the new version of the firmware onto that chip so that when the power is off, it knows what to do. It is true that you can do operating system updates on a computer. And when you do the updates, occasionally you'll have something that breaks. And updates are designed to fix things that are broken, but sometimes when updates hit, they actually break something else. And it's not uncommon for a lot of weirdness to start to happen on a system 2 or 3 years out into its useful life. One of the things that I want you to be painfully aware of is that if you get to the point where all of your operating system updates are intact and you have a clean system, you have an uninfected system, you don't have malicious actors on your system or malware or corrupted data, if you've eliminated all the other things, one of the important things to remember is that oftentimes, if you go out on the manufacturer's website, you'll find out, oh my gosh, there have been 10 new versions of BIOS. Man, 10 different releases of new BIOS for this motherboard, for this particular motherboard. I am going to talk about Uefi briefly, but we're going to get into more detail on that. Hackers found out a great way to park their malicious software inside the BIOS. So several years ago, they came up with a new convention to store the firmware and post protocols on a special, hidden, inaccessible partition on the hard disk, rather than the BIOS chip. It's called Uefi Bios. So instead of having a big chip with limited memory, there's just a couple of very quick digital components that prompt your system to look on the hard disk, but it's not on the C drive. What do I mean? On Windows machines, you have a C drive. It's the common drive letter. We used to have floppy disks that took up drive letter A and drive letter B. Long time ago in a galaxy far, far away, we reserved the use of drive letter A and drive letter B for floppy disks. In case you were wondering why it's always drive letter C. In Linux systems, we don't use drive letters. We just use a single / to represent the beginning of the disk partition, which is often referred to as the root of the disk partition, which is not to be confused with the root account or administrative, the first user account created when a system is put into service. Are we good so far? I'm unloading an awful lot of new information right now. Are we good so far?
Yeah, we're good.
Yeah,
And I hope you're finding this is kind of interesting, because as we get further out, we're going to get into some really cool stuff. Now, here is something I want to take some quality time. And I do want to express that what I'm about to explain is an oversimplification. And there are math professors that would hear this and go, okay, well, the probability thing you're explaining is kind of oversimplified. And if you're not careful, people get the wrong idea about how it works. I'm like, I know, but I want to give you a scenario where the use of logic gates can be used. Remember, we said that sometimes it makes sense for you to have a component with fewer logic gates, and it makes sense that you could have the same component with more logic gates, depending on the scenario. Have you ever heard the term, the house always wins?
Yes.
Okay.
Yeah.
The house always wins. We're talking about casinos now. Let's talk about gambling. One-armed bandits are slot machines. You pull a lever or push a button to roll the counters, and what you're looking for are matches. You want all of the items displayed on the screen to match. Put another way, you want each of the outputs on that slot machine to be true, or to be a certain distinct value. So it could be all cherries or all twos. The point is that you want all of the answers to match across the screen. When you do, depending on what they are, the payout is smaller or larger, depending on how rare it is. There could be 1 in 47 characters are cherries, depending on the slot machine. And of course, if they're all sevens, well, there's 10 different values, right? Well, numbered values, there's only 9 numbered values. You could have 0, 0, 0, 0 across the screen, but in slot machines, you might have all 1s, all 2s, all 3s, all 4s, all 5s, all the way up to 9s, right? So there are 9 of those possibilities are just plain numbers. And there could be so many sets of number 2 and number 7 and so on. Why am I telling you all this? Well, I want you to appreciate that I really am oversimplifying when I share what I'm about to tell you next. The house really doesn't win all the time unless they create addicts. See, gambling can quickly become an addiction because it's kind of a rush. When there's a payout, if you've put in a few quarters in a slot machine and then you get $500, that's a good day. That does an amazing thing to your adrenaline. There are all sorts of biological responses that hit. And those biological responses that have to do with the pleasure centers of your nervous system reinforce that habit. Gamblers and casinos, especially the people who own the casinos, understand this intuitively. It's not unlike drug pushers. So there's this chemical, this neurochemical known as dopamine, and it's a huge rush. When there's a big payout, it's a rush and it's exciting. And when people walk into a casino, there are video cameras everywhere. And why do we have video cameras everywhere? Well, they want to catch cheaters. But the more important thing is to catch the novice gambler, the newbie, the fresh meat, for lack of a better term. It's really good when people walk into a casino and it's obvious that, well, I mean, you can tell gamblers who are old hands at it. It's like, hey, this ain't my old, hey, Bill, hey, Betty, yeah, I'll have that cocktail that I usually do on the roulette table, right? The frequent flyers are what keep the casino open. But how do you build a cadre of frequent flyers? How do you build the population of addicts in our territory? Well, if you're new to gambling, they often give you a card. It's like a credit card. You can use it in slot machines. Okay? Is everybody with me? They have a booth. And you know, the cashier at the booth goes, "Oh, is this your first time here? Oh, well, we have a program for folks, you know, it's a discount card. Think of it as a discount card. Doesn't that make sense? I mean, you make so many purchases at a pizzeria, you get a free pizza, right? Or go to a restaurant, or you buy so many drinks, you get a free drink, right? What's not to like? Are you with me?
Yeah.
Okay. So what happens is that you get this special card to use in the slot machine. That special card says, hey, we have someone who's new. They haven't been in our casino. Another word for that is uninitiated, right? Now I want to share with you, you know what a truth table is. A truth table says, okay, out of 4 possibilities, only once with an and are things true. Everybody remembers this, yeah?
Yeah.
Yes.
So with 2 inputs, if you're using and, only 1 out of 4 times, if you're just randomly entering random ones and zeros, in terms of sheer probability, if your inputs are clearly and deliberately randomized, carefully randomized, and this is where the mathematicians would agree and they'd all be nodding, they'd say, okay, you're on track so far. 1 out of 4 times, you're going to get a true. If you take that functionality and you incorporate it into a slot machine, you'd say, okay, within 4 pulls of the handle, I get a payoff, right? And, you know, we don't want to be too obvious, do we? I mean, wouldn't it be too obvious if someone new to the casino pulls the lever, I don't know, 3 or 4 times? Oh, and they're always winning. But then you're looking around the room and you're like, all right, so what's going on with the rest of the people in this room? Well, the other ones that started coming 10 years ago, 20 years ago, and they're still here. And well, that one lost his family. This guy lost his house, right? There are true stories like this in every casino, right? But let's be honest, getting addicted to gambling is a lot like getting addicted to alcohol or any other drug. There are choices that people can make. What I want to ensure today in this class is a value-added life lesson that there are games that are intentionally rigged to ensure that people become addicted to gambling so that the house wins enough, it can stay in business. Okay, the house always wins. And what I want to do is share with you 2 scenarios with logic gates. Are we ready?
Yes.
So look at this first scenario. Now I've chosen to label the inputs. Can we see this?
Yes.
Yeah, we can see.
Okay, it's a little small, but let's get big. Yeah, let's make sure we get over here. So I've chosen to label the inputs for the first and A and B, but then to distinguish between them, C and D, E and F, G and H. We good so far?
Yeah.
Okay. And right here, function A and B, function C and D, function E and F, function G and H. Everybody with us?
Yes.
Okay. So 1 out of 4 times, this one's going to pop true. 1 out of 4 times, this one's going to pop true. 1 out of 4 times, this one's going to present true. 1 out of 4 times, this one's going to present true. Between them, when you have a probability of an occurrence happening between multiple sets, okay, so this is where we get into the language of formal probability mathematics. There are cases where you take the chance of this happening and the chance of that happening and the chance of this happening, and you add them together So if I pull the lever 8 times, I'm gonna, within 8 pulls, within 8 inputs, there's gonna be a true 4 out of 4 times. Now, let me say that again, verbally. If I have 8 inputs across these ands, based on basic probability, and are there cases where it doesn't happen nonetheless? Oh yeah, that's the whole point of probability, is that there's a chance that it should happen. And in this scenario, 4 out of 4 times, we're going to get a true. Now, everybody knows these W1, W2, everybody knows what those mean, right?
Yeah,
Okay, so these are the outputs of the ands, and these feed into what? What do you see here?
Doors.
or
The ors. So if 4 out of 4, I mean, in terms of mathematics, if you reduce, everybody knows what reducing a fraction is, right? So 10 over 20 is the same as 5 over 10 is the same as 1 over 2, right? So when I say 4 out of 4 chances is true, you can express that in different ways mathematically, but basically with 8 different inputs, the likelihood is almost 100% that you're going to get a true. When the true hits with one of these ands, it's going to flow into one of these 2 ors. Now, what you know about an or is that as long as there's a single true, what's the output of the or?
true,
Okay, and if one of these are true, then what's the output of this or?
true.
True.
Oh, yeah, true. But let's change it up a bit. Let's re-engineer or restructure our logic gates and what you have here is a set of double input ands inside. If we looked inside this, you'd see 2 input and running into another 2 input and running into another 2 input and. So what we've done is created an and here with 4 inputs. Is the truth table for this and the same as the truth table for this and? That's not a trick question. It's almost a rhetorical question. Would you expect the truth table for this and to be the same as the truth table for this and?
No.
No, absolutely not. It sounded like a trick question, but we only have 2 inputs. So 2 squared is what? 4. We have 4 rows. There's only 4 rows in this truth table. Everybody with me?
Yeah.
Simple
Yeah.
truth table here, right? What about this truth table?
16.
Yeah. 2 to the 4th.
4th. Yeah.
If we had 3 inputs, we'd have 8 rows. If we have 4 inputs, we have
16.
16. And here's the fun part. With 16 rows, how often is this and true? Is it 1 out of 4 times? Like the 2 input? You have 16 rows. What do you know about ands? In order for the output, in order for the output to be true, what has to happen with every one of these inputs?
They all have to be the same.
They all have to be the same. And there's only one row of the truth table where that's the case. The 16th or last row. Does everybody understand what I'm saying? Should I get out?
Yeah.
Should I get out a 16 row truth table and show you the truth table? And the first row is all zeros, the last row is all ones, and then you have all these different values. You have four columns. On the A column, you have half of them are zeros, half of them are ones. And the second column, you have, right, a quarter of them that are quarter of them that are zeros, a quarter of them that are ones, a quarter that are zero, a quarter that are ones. On the third column, you have like 2 that are 0, 2 that are 1, 2 that are 0, 2 that are 1. Everybody knows what I'm talking about, right? There's a pattern in the truth table.
Yeah.
Okay. If you're not, I want you to say so. Okay. So here's the magic. 1 out of 16 is true for this and. Put another way, every time we run random inputs, if they're truly randomized, only 1 out of 16 is the output of this and true. Now that's a different picture. And if I feed this wire into the top input of OR, and I have another one just like it down here, I have 1 out of 16 for this other function. And if I add the effect of those two together, I have a 2 out of 16 chance of being true. If true means you win on the slot machine, which one do you want to be in your, which one do you want operating if you want to win on that slot machine more often? This one or this one?
The smaller one.
Yeah, this one. If you pull so many times, oh, you want it to be true. What am I saying? If we use logic, if we use go ahead.
You continue.
If we use logic gates to build a slot machine and we're deliberate about it, we can have a digital component we turn on when the sucker walks in the door, the uninitiated new customer. And in so many pulls of the lever, oh, they're going to win. They're going to get that rush of adrenaline. But then after they've been there a while and they put some money in and their gift card runs out and the house needs to win so they can stay in business. Well, as long as the adrenaline rush is still active, as long as the dopamine is still there, it's like, you know what? If I put 50 bucks from my paycheck in there, I could bring home $5,000. No, you won't. I guarantee you will not. The house has to keep the lights on. The house will always win. What you need to understand is that there are some purely random things that happen in the casino. Now, a lot of casino attorneys would say, you are maligning the character and integrity of our establishment. And that is not fair, Professor Kentop. And I'm going to say, yeah, well, what you sell is a drug. It's a drug like any other drug. And it's good. Information is good. Information is power. Information is freedom. The truth will set you free. And we're dealing with a truth table. And I'm showing you a scenario where you can intentionally rig something in a game level so that people are giddy. They're so successful. Oh my gosh, cash in the savings bonds for our children's education. We're going to pay for that house by the end of the week. No, you won't. The house is going to open a whole new wing so that they can also allow people to bet on horse races. And before I get, cynical here about casinos, there's a lot of good that comes from the gambling industry. If people understand how it works, there's a lot of good that comes from distilleries, but not if you're a bad alcoholic and you can't be around a distillery. It's all a question about context. And I want you to be well informed. I want you to understand, B.F. Skinner, a famous, world famous psychologist, said, it's only the occasional payoff that's the biggest rush. The occasional payoff is like crack. It's like the worst kind of drug, because when you get a reward after occasional efforts, people go, well, I'm going to keep at it. And so they keep at it. B.F. Skinner established a long time ago, about 50 years ago, with some very important, renowned experiments, that if you reward somebody occasionally, it's very intoxicating. if you reward someone every time they pull the thing, every time they pull the thing, every time they pull the thing, they get bored and they walk off. Let me repeat that. If you reward someone every time they pull, every time they pull, every time they pull on a slot machine, they're like, okay, this is fun, but it's boring. And the house can't afford to pay out a lot more than what you put in every time, every time, every time, every time. It's a non-starter for the casino. It's also a non-starter for the gambler. The human nature or animal nature. He established this with rats, but we found out it's true with every intelligent organism on the planet. If you intermittently reinforce a thing, oh, that living organism learns very quickly to keep at it. Does everybody get what I'm saying? Keep at it, right? Keep doing it. You'll get a reward. Keep doing it. And that's why they keep at it. That's why they keep going back and going back. It's like, hey, I can tell the big payoff's going to happen. That's the part of this with human nature and logical design we want you to reflect on over the weekend. This concludes our class for the day. Are there any questions? Are there any questions?
No.
Okay.
Hey, Dr. Kentop, this applies to video games and their loot boxes too, right?
Oh yeah, that's a great question. You can intentionally design circuits, chips, that you, with the flick of a button, you can engage this or that, right? You can dial it up or down. Consider it like a volume dial on a stereo, right? You can dial up how often or how little somebody is rewarded. And that can be incredibly intoxicating. Especially if the people who are doing it are totally unaware of how this happens. Right? Somebody's gaming and it's like, hey, don't you think you ought to be getting some sleep? Oh, no, I'm almost at that next level. I got to get that next level. Well, you got to get some sleep too, because if you have an 8 o'clock class and you're a moron in your 8 o'clock class, that's not going to end well. Oh, but I'm almost done. I'm almost done. I'm almost there. Does that sound familiar? Is that ringing any bells for any of you? I have 2 sons. They would be throwing. I have 2 sons and they'd both be throwing things at me right now. If they heard this, if they heard what I just presented, they'd both be throwing stuff at me in the room. They go, Dad, enough. I don't want to hear any more. But I just want you to know. I want you to know. Knowledge is power. Truth will set you free. All right, I'm going to stop sharing and stop recording, and then we'll ask if anybody has any questions off the record.